Could there be DMI? You make a guess. Yeah. Could there be the DMI?
Yes, if you displaced.
Displaced in which direction?
If we put strain, or if we introduce defects.
Yes.
So it has to be dissimilar.
Yeah, that's a very good answer. Yeah, and that's the correct way of thought. So if you introduce strains or defects, then you could make the midpoint of the nearest neighbor no longer a inversion center, breaking the inversion symmetry, therefore inducing the DMI. But without the strain, without the impurities, then intrinsically the DMI on first nearest neighbor links is forbidden because the midpoint is a inversion center. However, even intrinsically speaking, without impurities, without strains, the second nearest neighbors already breaks the inversion symmetry. So the midpoint of the second nearest neighbor link is no longer this is not a inversion center, because if you stand on this point, what appears on your left-hand side and what appears on the right-hand side are different. So the inversion symmetry is explicitly broken. Therefore, even intrinsically, you could have a DM interaction connecting second nearest neighbor links. So now let me ask you a question. So what is the DM vector? In what direction is the DM vector associated with the second nearest neighbors? Or the people sitting on the back, I hope you could be more interactive. Any answers from the back? No answer? Okay, so we could still apply, this rule. So, because standing here, you observe a twisted atomic bonds. So the DM vector is the cross product of the two links. So it's pointing outward. But that way, you could only determine the direction up to a sign. The DM vector could either be pointing into or out of the board. Okay. You should.
Sorry, I have a question, but maybe you can finish your part first.
I'm sorry?
I have a question, but maybe you can finish this small part first.
For this, yes, I just finished it. Yeah,
okay,
please.
So I have a question about the relationship between DMI and RKKY, because I've seen experimental papers that claimed they say the DMI is an extension of RKKY.
Okay, so here's the thing. So there are two ways to classify the magnetic interaction. One is the geometrical classification, the other is basing on the microscopic mechanism. So the RKKY, the super exchange, those are related to the mechanism. But the DMI is actually defined geometrically against the isotopic Heisenberg. So for example, you could even write a matrix unifying the Heisenberg with the DMI interaction, and those terms appear on the off diagonals. Well, the Heisenberg terms appear on the diagonals. So I would personally, understand the DMI as a geometrical extension, as an antisymmetric, extension of the isotopic or symmetric Heisenberg interaction. So, yes, there could be RKKY associated with, DMI associated with RKKY, but I think there are, more cases where the DMI comes together with the super exchange. Yeah. Mm-hmm. Question?
So the JJ and the exchange parameter can be a tensor, but like the Heisenberg exchange and the DMI interaction, it is a scalar. How can we reduce this tensor into a scalar?
Okay, so I think now is the point that I should write on the board. I would just shout, So I would. temporarily remove my microphones. Okay, so for the Heisenberg interaction, you could just mathematically try to unify the two terms into the same term. For example, you write S1x, S1y, and S1z times JH, times and S2x, S2y, and S2z. Well, the DM interaction fills up, for example, this x couples to y, therefore you could call this dxy, right? And this is dxz, and this is dyz. Now, this should be an anti-symmetric matrix. So the yx components is actually minus xy. So this is the way that we put everything into the same matrix. And computationally, you could quantify each element in this 3x3 matrix, out of the same calculation. So what is being written here, this is a universal D shared by all components. But in principle, those three components could be slightly different. But I mean, my intention is not to, overwhelm you with too much detail. Yeah. Any other questions? Mm-hmm.
So when you were talking about this RKKY coupling, so it has this oscillatory nature.
Yeah.
But what exactly happens when it crosses from ferromagnet to anti-ferromagnets? I mean, like how our spins are aligned at that moment? Because,
Oh,
yeah.
okay. So you mean for the RKKY? So you are asking what happens if I stand right on the turning point, right? That's a good question. So the system becomes magnetically very unstable at that point, because an infinitesimal perturbation on the lattice will result in a substantial change of the magnetic ordering.
Okay. So the spin's orientation will be randomly at that point. Is it correct?
Yeah, I mean the system has the possibility to suddenly turn from an antiferromagnet into a ferromagnet, or vice versa, if you could prepare the system right on the point.
Okay.
Yeah.
And one more question, like when we are talking about this J, when it's negative, it's anti-ferromagnets, when it's positive, it's ferromagnets. But like what microscopic parameters defines J's sign? So I mean like when it is positive or negative?
To answer that question, we should also, turn to the specific models. For example, in the super exchange, if I'm talking about this, I cannot write down this one. So the super exchange depends on, the t square over u, where t is the hopping parameter, where u is the on-site Coulomb repulsion energy penalty. And there's always a minus sign associated with this. So that's why the super exchange always turns out to be antiferromagnetic. But I mean, we could spend a couple of hours just try to quantify the super exchange. But a short answer is that the super exchange, for example, microscopically depends on the hopping energy squared divided by the on-site Coulomb repulsion. Yeah.
Yeah. So one last question, like there was an equation where this DMI and exchange interaction, they both like compete, then they can like twist the spin structure. I mean like there may be some competition in between that. But if in a system there is only exchange interaction and dipolar interaction, so as you have mentioned that dipolar interaction is quite less than exchange interaction, but how dipole interaction can significantly change the magnetic structure in that particular system? I mean like what role it has in a system, because it is very less than exchange interaction, but still in some cases we read that dipole interaction changes the structure and all.
Yeah, that's a good question. So to answer your question, let me directly jump to the last part of today's presentation is magnetic domain walls.
Okay.
So the exchange interaction is much stronger, but at the same time it's a short range.
Oh.
But the dipole interaction is much weaker, of course, but it's also long range. So if you consider a large size of material, then in the long range, it is the dipolar interaction, the weak one, will dominate, under which the materials will break up into multiple domains. So, I mean, this is, I just jumped through different sections of my talk.
Thank you so much.
Mm-hmm.
Could you explain a bit about the bond, how the bond angle playing a vital role in the
I'm sorry, I didn't.
how the bond angle playing is a vital role in the super exchange interaction.
In the
Suppose you are saying the super exchange interactions give to the antiferromagnetism.
Mm-hmm.
So this is some kind of D and some like a O and D. The bond angle is 180 in that case. Okay. Now I am talking about the bond angle between the three atoms.
Okay, the three atoms.
Yeah. So how these bond angle playing a vital role in the indirect exchange interactions?
In the direct exchange. That's a good question. So how does? Well, the thing is, I mean, for the super exchange, it's easy to define the bond angle because there's an intermediate site. But for the direct exchange, well, because it is direct, the two atoms are just directly overlap. So then it's hard to define a bond angle because there's not another atom between them. You could say that the bond is still straight.
Okay. And for in the next slide.
Next one.
Yeah. Suppose in the bond angle between DPD is 180. And in the another case, the bond angle is DPD is 90. So what is the difference between these two?
Oh, for example, for in a straight or a perpendicular case, right? Then for the perpendicular case, we are expected to have a DME interaction if there is a spin-orbit coupling.
Okay.
I mean, inversion symmetry is broken and substantial spin-orbit coupling. The combined gives you a DME interaction.
Okay.
Yeah.
Thank you.
For example, in some materials, you have a strong spin-orbit coupling here, but the bond angle is, zero. Still, you do not have DMI. And in some materials, the bond is highly twisted, but the spin-orbit coupling is too weak. Then the DMI interaction is negligible. Two conditions. And sometimes, the two conditions are not independent because the spin-orbit coupling is somehow locally induced by the broken inversion symmetry. So, yeah. Any other questions? Mm-hmm.
Sir, I know you're giving us a general picture overview of it, but what kind of determines the spin-orbit coupling? And I'm not talking about mathematics, but just a visual picture to help me visualize things here.
What determines the spin-orbit coupling?
Yes.
Physically speaking, I mean, the heavier the elements, then the larger, generally speaking, the larger the spin-orbit coupling. For heavy elements, you will generally have a larger spin-orbit coupling.
Okay, so that's the general trend.
General. I mean, to answer this, your question in a short way, yes. For example, in many materials, we hope it could have a strong enough spin-orbit coupling, but it turns out to be the opposite because the element is so light.
Okay.
Yeah. For example, one of the materials that we have been studying for years is chromium triiodide. This is a very famous two-dimensional honeycomb ferromagnet. Well, it's a layered antiferromagnet. We have been playing with a lot of models, assuming a DME interaction, until we eventually realize this material can hardly have a strong enough spin-orbit coupling. because the chromium is not a heavy element.
So spin-orbit coupling
Yeah.
is a determining factor whether a material will have DMI interaction.
Yes, I mean the DMI certainly does require a strong spin-orbit coupling, yes.
Okay, thank you very much.
Yeah. All right, since we're seriously behind the schedule, I think I should at least finish my lecture 1. Therefore, let us proceed with the next topic, the magnetic order. Okay, so having talked about the exchange interactions and in general the spin-spin interactions, then we claim that an interacting spin system is able to order on itself without the aid of external magnetic field. And that defines the ferromagnetism. Okay. So, well, in general, the magnetic ordering, without the application of a magnetic field, is known as spontaneous magnetization or spontaneous ordering. So, spontaneous ordering is a profound concept in condensed matter physics. And here in our context, we apply the idea to the spontaneous magnetic ordering. We know that it is exchange interaction, coupling different spins, that eventually drive the spontaneous magnetic ordering. So once the magnetic material is ordered, then we could classify the magnetic ordering by a quantity known as the order parameter. Okay, the order parameter. So the simplest magnetic ordering is called the ferromagnetism, where the magnetic order could simply be taken as the average density of magnetic moments or magnetization. So magnetization serves as the order parameter for characterizing ferromagnetism. And we also have the antiferromagnetism. As I mentioned, this was Louis Néel who gave this name. Before him, the antiferromagnet was known as the anisotropic paramagnet. But actually there is spontaneous ordering, so strictly speaking, it should not be regarded in any way as a paramagnet, because there's a spontaneous ordering at a finite temperature. And antiferromagnet features opposite spins within one unit cell. So within one unit cell, you have opposite aligned magnetic moments, but if you subtract one spin from the other, you could still define the order parameter to characterize the material, and this is known as Néel order. And there's an intermediate case called ferrimagnetism, which is somehow shares features from both ferro and antiferromagnetic materials. So within the unit cell of a ferrimagnet, we need two quantities at the same time. We need the magnetization and the Néel vector, because the two spins are either chemically inequivalent they are typically chemically inequivalent. But even if they are chemically similar, they could exhibit, because of the different crystal environment surrounding the different atoms, they could exhibit physically different magnetic moments. So this is a ferrimagnet. And yet there's spin spiral, or more generally spin textures, especially when the DMI is taken into account. So this consists of a separate topic. So today, unfortunately, I may only have time to talk about the simplest case, ferromagnetism. But the good news is, if you are interested in antiferromagnetism, you could still get in touch with me after the lecture. My research group is primarily focused on the study of antiferromagnet. But today, I won't even cover antiferromagnet. Okay, so ferromagnet. All right, so the simplest model to characterize the simplest model to understand the spontaneous ferromagnetic ordering is pioneered by Curie and Weiss, and this is known as Curie-Weiss mean field theory. We know that a group of interacting spins could effectively be described by a Heisenberg interaction, where the Heisenberg exchange could be very, very large. So the spins are apparently coupled. The key idea underlying the Curie-Weiss model is to define what is known as a mean field in order to decouple the spins. For example, the spin Si is interacting with all its neighbors through the Heisenberg exchange. And here I even didn't specify the microscopic mechanism of the Heisenberg. It could be RKKY, it could be direct or indirect, super exchange, whatever. But the thing is, Si is indeed interacting with its neighbors. But basing on the mean field approximation, we could recast the exchange interaction into a mean field. And the mean field is proportional to the average the magnetization in a way such that the spin Si is now interacting with the mean field rather than the spins surrounding it. So this is a simplification that mathematically decouples the spins in an otherwise strongly interacting system. So under the mean field approximation, a ferromagnetic interacting system now becomes effectively a paramagnetic non-interacting system, but the price you pay is now the effective paramagnetic system not only interacts with a real magnetic field, but also interact with the mean field as an effective interaction. But we should always be borne in mind that the mean field simply captures the spin-spin interaction. It simplifies the spin interaction into a mean field, which transforms the coupled ferromagnetic system into a decoupled paramagnetic system, paying the price of introducing the additional mean field. Now, with the mean field approximation, we could solve a ferromagnetic system basing on our knowledge of paramagnetic system. We already know that in the previous section. We already know how to solve a paramagnetic system. Now this is effectively a non-interacting paramagnetic system, as long as we take into account the mean field. So now we are ready to solve the system as effectively a paramagnet in the presence of the mean field. And we are seeking for the solution at a zero magnetic field, because we would like to see if the system could magnetize on its own without the magnetic field. So now, because the mean field itself depends on the magnetization, and we solve the magnetization basing on the mean field model, which indicates this is a self-consistent system. Okay? So you have the unknown variable m on both sides of the equation, the Brillouin function. So we could numerically solve the system, but now I would like to introduce a heuristic method called the graphical method. So the blue curve plots the Brillouin function for a given total angular momentum j. Well, in terms of the new variable y, well, with the zero B field and only the mean field only, then the left-hand side of the self-consistent equation is represented by a straight line passing through zero. At a high temperature, the two curves only intersect at zero, which means zero is the unique solution of the system. The solution simply represents zero magnetization. As you're lowering the temperature, then you are lowering the slope of the left-hand side in terms of the y variable, until eventually the line is tangential to the Brillouin function on the right-hand side. This point marks the transition. I mean, this is a critical point below which the two curves intersect. It affords two opposite solutions and finite solutions. So the self-consistent solution of the mean field model predicts that there is a finite transition temperature Tc, below which the system is able to develop a spontaneous magnetization. Okay. spontaneous ferromagnetic ordering. That transition temperature is known as the Curie temperature. Okay, the Curie temperature. So the Curie temperature in transition metals is typically very high. It's on the order of a few hundred to even 1,000 Kelvin. It's way above the room temperature. And that is directly attributed to the large value of the mean field. But as I emphasized, the mean field represents nothing but the spin-spin interaction. So the mean field is not actually a field. It is an effective concept representing the strong Heisenberg interaction. That's why the mean field could be as strong as 1,000 Tesla. Well, for real magnetic field, I don't think it's practical to have a 1,000. Okay. Okay, so this is the mean field, the self-consistent solution. Any questions? Hmm? Oh, we go first?
What's the value of lambda?
Oh, the lambda, lambda is a phenomenological parameter. So the Curie temperature Tc is proportional to the phenomenological lambda. Because the Curie-Weiss is a phenomenological model, therefore by experimentally measuring the Tc, you are able to quantify the lambda. But you could still understand the lambda as arising from the Heisenberg. So it's basically proportional to the Heisenberg exchange. But the thing is, the key point is that the Curie-Weiss model does not even depend on the microscopic details. You do not have to know the Heisenberg interaction in order to apply the Curie-Weiss model. Yeah.
Thank you.
Any other? Oh, you have a question?
Thank you. So my question is, you just explained that the main magnetic field could be as large as 1,000 Tesla.
Mhm.
That's kind of inconceivable for me in a practical notion, because that's like 1,000 Tesla.
That's why we call it effective field, not a field. This is an effective magnetic field stemming out of the microscopic exchange interaction.
But if I am visualizing, and correct me if I'm wrong, if I'm like a spin, an electron, and I'm experiencing this 1,000 Tesla, so when you're doing this approximation here, it's just saying that instead of just talking individually to other electrons, I have maybe just talking to one person very loudly. That's how I'm visualizing the mean magnetic field. Isn't it approximating like all the interactions?
Yeah, all the neighboring interactions.
To
But
just one huge field.
so here's the thing. So the Heisenberg interaction J, is a spin-spin interaction. However, according to our direct or indirect exchange, the true physical origin of exchange interaction is purely electrostatic. It's a Coulomb interaction. It's not even related to spin. It only effectively couples to spin by simultaneously minimizing the Coulomb interaction and satisfying the fermionic statistics. So here, the Heisenberg interaction couples spin. It's a spin-spin interaction. But our starting point has nothing to do with the spin other than the Pauli exclusion principle serving as a constraint. So the interaction has a pure electrostatic origin. And the electrostatic field could be way more stronger than the magnetic or spin-spin interaction. And we have a heuristic understanding. For example, in the electromagnetic wave, the electric field component is larger than the magnetic component by a speed of light. And that is a very large number. So, this is a heuristic, non-rigorous understanding. So, because the Heisenberg interaction is attributed to a pure electrical origin, it's not a spin origin, spin is an effective picture. The true physical origin is electrostatic, which explains why it could turn out to be effectively as strong as 1,000 Tesla.
Okay, so if I am getting it right, what you are saying is that it's actually taking the electrostatic interaction.
Exactly.
Mostly
It's the manifestation of electrostatics
static and the
on the
spin.
spin degree of freedom.
Okay.
Yeah.
Okay, that makes sense.
I like the word manifestation. So it's a manifestation of electrostatic interaction in the spin degree of freedom.
Spin degree of freedom. Thank you very much.
If we have a pure spin, then 1,000 is like a joke, right?
Yeah. Okay.
Okay. All right. Okay, so this is the Curie-Weiss model, the mean field model. So actually, based on the mean field model, you could, quantify the magnetization as a function of the temperature, all the way from 0 to the Curie temperature. So this is just a plot with the temperature scaled by Tc. So 1 represents the Curie the transition temperature. Well, the Curie-Weiss model is pretty successful in explaining the spontaneous ferromagnetic ordering. It also suffers from a series of problems. For example, if we push to the 0 temperature, then the mean field theory predicts a exponential decay. Exponential asymptotic behavior towards the saturation. However, experimentally, we get a different answer. Experimentally, if you fit the experimental curve, then the magnetization approaches saturation following a power law instead of an exponential law. The discrepancy is attributed to the negligence of spin fluctuations in the mean field. So to properly account for the experimental observation of the power law in the low temperature regime, then we have to go beyond the mean field model and look into the spin excitations known as magnons, which certainly I won't have time to talk about today. So within the mean field treatment, we could also, extract information for a finite field. For example, in the paramagnetic phase. So this is the Curie temperature separating the ferromagnetic phase from the paramagnetic high temperature phase. So even in the paramagnetic phase, if you apply a magnetic field, you could still induce a finite magnetization because the system is now paramagnetic. So in the presence of magnetic field, no matter how small it is, then you will immediately remove the discontinuities in the slope of the curve around Tc. So, the ferromagnetic Curie transition is a phase transition, a continuous phase transition. In the presence of a finite magnetic field, this becomes a crossover rather than a phase transition. Okay, so this is a key point. You will immediately remove the phase transition point by even an infinitesimal magnetic field. Okay? So in the presence of a finite magnetic field, we could also rid off the